Okay, so today we are doing 3.7 motion, and notice it is day one. Some things to point out is notice your homework is page 132, 1 through 10 all. If you flip over to the bottom of your notes, or to the back and the bottom, you'll notice in some fine print down there are the even answers for you to check. Okay, so 2, 4, 6, 8, and 10 are there for you to check. The odd ones are still in the back, but because we're just going to start off slow with some motion problems. All right, so our objectives today is to solve problems about related distances using, we have another formula, D equals RT. All right, D stands for our distance, R is the rate, which is always it's always been a percentage, okay, but we're talking about distance. So what are some rates when we talk about distance? Traveling distance. Okay, not miles, but miles per hour. Okay, what's another one? Feet per minute, sure. Kilometers per hour, nice. Kilometers per minute, possibly. You might see meters per minute. Okay, what would you say? Okay. All right, so in this case, our rate is going to be more of a fraction. Okay, we've talked about ratios and rates earlier on. So these rates are not per 100, but they're using the two different units. Okay, and time, in this case, for traveling distance, time can be anything. Okay, it can be minutes, it can be seconds, it can be hours, it can be years, it can be days, whatever. There are no limits to the time here. Okay, often you can simplify motion problems by making a diagram and a table. That's what we've been working on for a while now. We're going to try to keep using that. We're going to fill the known quantities into any horizontal row, then find the unknown quantity by using the formula. RT, or R times T, equals D. And bless you. All right, so this box, right, this table, we're just trying to plug in. Like I've given you 3 examples. I want you to look at how this looks. So it says, how far will a car travel if it goes 50 miles per hour? What is this? My rate or my time or my distance? Rate, so that's why it's in this box, for 3 hours. That's our time. So that equals D. Okay, so 50 times 3 equals D. Well, what is D then? So this would actually be 150. We could put 150 in there and solve it if we're given both of those. Okay. Then on our next one, it says how far will it travel if it goes 50 miles per hour? So what's that? My rate, my time, or my distance? The rate again for T hours. Well, my time now is T. So my distance is equal to 50T. Okay, so just getting that equation or that expression, 50T. At some point we are going to answer it, but we're not there yet. Okay, just trying to figure, again, like put the stuff in the table. Okay, at what rate? So this time it's saying at what rate? Well, what does that tell me? We don't know the rate, so that's why we put an R. Okay, is a car traveling if it goes 225 miles? What's the 225 miles? That's the distance. That's how far it traveled. Good. In 5 hours. And that's our time. Say what? No, because if we wrote this into an equation, R times T, so this would be 5R equals 225. I would divide both sides by 5. So my rate would be 45. 45 miles, because we went for miles, per hour, because we went for 5 hours. Good, so that would be our rate if we needed to solve it. Good. Perfect. So just, again, practicing using what. Okay, so you're just practicing putting the numbers in the chart. Like that was all that really was for us to get there. All right, so now we're going to talk about these uniform motion diagrams. Okay, when we're talking about uniform motion, actually, let's look at a couple of the problems on the back to get an idea of what we're talking about. Okay. Example 1 says the junior high and the high school Sunday school. Okay, you'll have to pardon this screen. We're having technical difficulties. Let's see if we can get back there. Okay, so the junior high and high school Sunday school classes are going on a hike. The junior high class leaves the church and travels east at 3 miles per hour. The high school class leaves an hour later. Pardon me, traveling at 5 miles per hour on the same route. How much time will pass before the high school class catches up with the junior high class? Okay, this is a motion problem. It's people or planes or cars, whatever, in movement, in motion. Sometimes they're traveling the same way, like here, the high school class, they're taking the same path, they just left later. Okay? Example 2. 2 trains leave Mattoon at the same time. The northbound train travels 5 miles per hour faster than the southbound train. So we're headed 2 different directions. They leave the same place, headed 2 different directions, and at different rates. What's the rate of each train after 3 hours if they are 333 miles apart? Example 3. John, a senior on the track team, runs at a training rate of 375 meters per minute, while Paul, a freshman, trains at 325 meters per minute. How long does it take for John to lap Paul if they are training on a 400-meter track? How many laps has each run during this time? Okay, so they're leaving, right? They're training for track. They're leaving the same place at the same time. We're running around the track, and we're just seeing how long it takes for the faster guy, the senior, to lap the freshman. Okay, so these are motion problems. Does that make sense why they're called motion? Okay, perfect. Then let's go back and look at the motion diagrams. Okay, so there's 3 different setups that we're going to use for motion. Okay, the first one that we use, and I'll kind of draw a squiggly line across here, maybe to help us see it, okay, is we call them round trip or pursuit. So when there's a round trip happening or someone is in pursuit. So this is saying when we have a trip to and from somewhere, your trip to and from work, to and from school, okay, wherever. Or when the second person leaves to catch up to another person. The key here is that they're traveling the same distance. So we say distance 1 is equal to distance 2. Okay, in these cases, the 2 distances, we're going to set up the formula or the equation where the expressions are equal to each other. All right, for the next one. Okay, this is when we have motion in opposite directions. Okay, or we're traveling from separate locations to meet. That's what this diagram is showing. So this person, D1, is leaving from here and they're meeting. Okay, D2, the other person, the other distance, is leaving from there and they're meeting in the middle. Okay, that's one example. The other is when we travel in opposite directions from a common location. Okay, so here's our common location. And so one is traveling east and one is traveling west. Okay, we're traveling in opposite directions, but then they're giving us the total, we sometimes have that total distance, the n down there. In this case, we sum the distance. Okay, so that's why in this equation we have distance 1 plus distance 2 equals that total distance of n. Okay, so different problems call for different setups of the formulas. Okay, our last one. Okay, this one is when we're given the given distance must be added to a shorter distance to equal a longer distance. So if we look at this diagram, so we can be given distance 1 is longer, and then we have our shorter distance that we were given, and we have to add it. Like, so maybe if we're going on a trip, like if I was going to see my sister, maybe I would drive to Columbia and pick up my mom or meet my mom, and then we would go on to Brazito, Missouri to meet my sister, which is south of Jefferson City. Okay, she lives south. But maybe, so then we would figure out the distance that I traveled and the distance that my mother traveled. Okay, so we're giving 2 different distances. But I could tell you the total distance is 200 miles or something like that. Okay, it's the same setup here. It just depends on what order you're given it. But you're given one long distance, and then maybe somebody drove part of the distance, and then they stopped. So maybe I left here with my kids. Okay, we left and we drove to Columbia, and I left my kids with my mom, and then so how far my kids traveled was 40 miles less than what I traveled. Okay, so we have that different thing there. In this case, we have D1 equals D2 plus the new or the unknown, that shorter distance that we need. Okay, so we're given different pieces of information, so we have to set up our equations differently. Okay, so you're going to be flipping this sheet back and forth today, over and over and over again. All right, then solving uniform motion problems. There are some keys here, and this is not just uniform motion. This is any word problem at all, some skills that you can use to help you. All right, so first, we need to read the problem carefully. Okay, identify the main unknown in the problem and let the variable stand for this unknown. That's what we've been working on for days, like even this morning in first hour when we were going through some of the problems from homework, going through these. B, draw a diagram to represent the problem. We're going to start doing that more today. 2, plan a strategy. Make a table. Okay, that's what we've been doing. Fill in the rate and time columns. One column will contain specific numbers from the problem. The other will involve an expression, okay, using the table. Okay, that's what we're going to do. We're trying to get that expression for distance. Rate times time equals distance. So we're going to use the R times T equals D. We're going to fill in the distance column. Solve an equation. We're using this to convert to an equation. Use your diagram to help you write an equation relating the distances and then solve it. And then step 4, check. Did you answer all the questions in the problem? Did you interpret the answer using proper units? Much like with the questions we were going over, and I said, okay, we're solving for time. Should we get a big number this time? No, and you guys, like we thought through that. Like principal, yes, we got a bigger number. Time, no, we're going to get a smaller number. Okay, and then are our answers reasonable? That's that same thing. Let's go hand in hand. Okay, so flip over to the back, and we've got example 1. The junior high and high school Sunday school classes are going on a hike. The junior high class leaves the church and travels east at 3 miles per hour. The high school class leaves an hour later, traveling at 5 miles per hour on the same route. How much time will pass before the high school class catches up with the junior high class? We are not solving these today. Okay? We are going to answer the question, which diagram and formula do you use? And we're going to draw a diagram. That's it. Like, I want you to understand the problems. So, which diagram do we use for this first one? The same distance, he says. Round trip or pursuit. Do you guys agree with that? On the front side. It'd be same distance? Okay, so let's draw. So we're going to say same distance. Or it was the round trip pursuit, right? Whatever you want to call it there is fine. Okay, so let's draw a picture of that, of what is happening. Okay, so we've got our starting place, right? We're leaving to go on the hike. They leave the church. Okay, this is the junior high class. They leave the church. They travel east at 3 miles per hour. So we can say we can write that in on there, 3 miles per hour. Then the high school class leaves an hour later. Okay, so we've got, I'll just put HI for high school. They leave traveling the same thing. And how much time will pass before they catch up? That's where that other line comes from, like they've caught up. to each other. We know they're traveling 5 miles per hour. And what else do we know? That's not all. Huh? They're going on a hike. That's not really helpful for our distance, rate, and time. Those are the... Yes, because that deals with time. So that's important. So they left 1 hour later. Does that diagram look like the same distance in round trip? Okay. Okay. So what formula do we use? Nope, nope, nope. No numbers. No numbers. So we're going to take the junior high. Go back to the pursuit. Go back to the front. Go back to the pursuit. Okay, so the junior equals the high school. No, because we're changing D1 and D2 to junior equals the high school. So the expression that we get for the junior high is going to be equal to the expression we get for the high schoolers. Okay? That's all we need to know at this point. We're going to set them equal. Perfect. Okay? All right, let's look at example 2. 2 trains leave Mattoon at the same time. The northbound train travels 5 miles per hour faster than the southbound train. What's the rate of each train if after 3 hours they are 333 miles apart? The sum, good, the sum distance formula. Okay, so sum distance. Okay, so let's look at our diagram for that one. Or what is this? So it does say sum distance. What is that also called? Like earlier we had round trip pursuit. So motion, this is opposite directions. Okay, good. All right, so we've got opposite directions going on here. So where should we start? Okay. Where should I draw my line? Over here or in the middle? Or okay, if they're traveling in opposite directions, if I draw my line here, my diagram is going to go this way and that way. Right? Like Mattoon should be here. Does that make sense? Okay, one is traveling north. So this is my northbound train, we'll say. That doesn't look like an N because my board is not calibrated. Okay, the northbound train we know is traveling 5 miles per hour faster. 5 miles per hour faster. So I'm just writing some notes. Then the southbound train. Okay, well, my southbound train is going this way. Goodness, I do need to calibrate my board. All right, what is the rate if each train, if after 3 hours they are 333 miles apart? Ooh, see, that gave us our total distance from here to here. This distance is how much? Yeah, this is 333 miles. Okay, so that's helpful to know. And we know that they travel for 3 hours. Bless you. Okay, so what would our formula look like here? M is Mattoon. This is the place they left from. I'd equal that total distance at 333. Awesome. Good. Yeah. So just trying to make sense of what's happening in each of the problems and how we set up the formula. Good. Good, good. All right, let's clear it and we'll move down to 3 and 4. Okay, so example 3. John, a senior on the track team, runs at a training rate of 375 meters per minute, while Paul, a freshman, trains at 325 meters per minute. How long does it take for John to lap Paul if they are training on a 400-meter track? Would it be same distance? What do you think same distance? Okay, then I heard the last one. That given distance must be added to the shorter distance because we want the senior to lap Paul. So that means he's going to run farther, right? So would it be the same distance that they're running? Okay, but that's a good one. That's what a lot of times, like, this one is probably the hardest one to think about because we also, when they're running on a track, what shape is their distance? Oval, right? Like they're running in circles. So we don't think about the distance as a long, like a straight thing from Mattoon north and Mattoon south, okay? Or from leaving from the church and going to their hike. We think about them running in a circle, and so it's harder to think about the total distance ran. Good. This is that last one though. So the given distance shorter, we can call it. Okay. All right. So how are we going to think about this one? Because they are starting from the same place, right? On the track, they start from the same place. So John is the long one. Okay, so we got John. I'm just going to put a J. He's running the longest distance. Okay, we know his rate is 375 meters per minute. Okay. So what do we know about Paul then? His is the shorter distance. And he's running at 325 meters per minute. How much shorter is his distance? 50 meters? How do you figure 50 meters? No, that's his rate. His rate is 50 meters per minute slower. This is true. How'd you get 400? Keep going. Excellent. Okay, you want to know how long it takes John to lap Paul. They're running on a 400-meter track, so a lap is 400 meters. Good. So that he was running 400 meters less. Paul is running less than John, 400 meters less. So what would our formula look like? Perfect. Yes. Awesome. Because John is running the longer distance, so his distance is going to equal Paul's distance plus 400 meters. Okay, perfect. Last one. Okay, Mr. Rogers leaves Roseville for Milltown, traveling at 48 miles per hour. Mr. Brown leaves Milltown for Roseville at the same time, traveling 50 miles per hour. If Roseville and Milltown are 294 miles apart, how long does each man travel before they meet? Same distance? Okay, if we don't know, let's draw a picture. Mr. Rogers leaves Roseville. Okay, so we've got Roseville here, and he is headed for Milltown. So he's going to Milltown. All right, but in Milltown, we've got Mr. Brown leaving Milltown for Roseville. Okay, so what's happening there? They're going opposite directions. So this is... Okay, we would sum the distance because it's opposite direction. Okay, so opposite direction. We're going to sum the distance. okay, because they're traveling the same. But here's the thing, it can be misleading if we draw them separately, because we want them to, are we wanting to find how long it takes them to get to all the way across? No, we want to find how long before they meet. So they're going to Roseville, this one's coming this way, okay? This is more it, more the description. Where do they meet? And then we know their total distance was what? 294 miles. All right, and so we've got, let's see, Mr. Rogers. So we'll call that Mr. Rogers is going 48 miles per hour. And Mr. Brown is going 50 miles per hour. But we want to know how long before they meet. So what would my formula look like? Using that, what's opposite motion in opposite directions, knowing that we sum our distances, it's going to look like what? Okay. Yep. That's right. Okay. And that's all we're doing today. None of your problems for homework are going to be using any word problems. They are all just using the formula D times R equals, or R times T equals D, or D equals RT, however you want to look at that. Okay. Yep. Yep. So yes. So you're going to take those, because yeah, in 1 through 10, you're given that table with your distance, your rate, or your time. And you're just plugging those into your equation and solving. You're not actually doing any word problems. Tomorrow when we come back, we're going to go through the word problems, and we're actually going to put them in the table, and we're going to work on solving them in class tomorrow. Okay? You have 13 minutes. You can work on homework.